Hello my dear students, very good morning. Welcome to Electronic Devices and Circuits course. This is Dr. Pandu Rangaiah, Associate Professor, Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering. So my course title is Electronic Devices and Circuits, and in this session, today's session, we are going to discuss about what is an introduction to the amplifiers and also the H parameter model of a transistor. And after completion of this session, the students are able to know that what is an H parameter model of a transistor, and also they are able to draw that on their own, the H parameter model of the transistor in a common emitter, common base or common collector configurations. So now let us know that before going to that the sessions, actually we know that what is the definition of an amplifier. An amplifier is a device which increases the strength of the AC signal without changing its shape, that is without changing its frequency. Means an amplifier is a device which increases the strength of a weak signal in terms of amplitudes, whether it may be a voltage or current, without changing its frequency in the output is called as an amplifier. To make the transistor to use as an amplifier, the transistor must be operated in active region. That is, to get the amplifier action, the transistor must be operated in active region. Active region is nothing but the base to emitter junction is forward bias and collector to the base junction is reverse bias. So we need a biasing circuit to make the transistor to operate in active region before to use the transistor as an amplifier. So then there are the different types of biasing circuits are there. Out of that, the fixed bias or collector to the base bias and self bias circuit. The self bias circuit will give the more stability to the operating point. Therefore, all the amplifiers are used to be designed by using a self-biasing circuit to make the operating point onto the DC load line. So the biasing circuit is needed to choose that a stable operating point onto the DC load line. Okay. So where again to get that the operating point will be very stable, and also it must be to get thermal stability, where we can use the conditions of VCE is less than VCC divided by 2. So before using the transistor as an amplifier, to get the thermal stability, faithful amplification and stable operating point, we will follow that all the prerequisites and we will choose the operating point onto the DC load line appropriately at the middle of the DC load line, such that without any distortions, we will get it is a faithful amplification at the output. Now here this is a transistor AC load line where the operating point will be chosen at the middle of the DC load line, and where we will apply it is an input. By applying it is an input AC signal, due to that the IB current is increases. As IB current is increases, because of the transistor action, IC is approximately equal to beta times of IB. Therefore, IC current will be increases to a large extent, and the output will be the AC signal will be applied at a larger amount, larger amplitude. So, for that where we'll apply it is IC is equal to beta times of IB. Therefore, where the collector current is increases. As the collector current is increases, a large current flow through that across the collector resistor, and which appears a large voltage across the collector resistance. Thus, a weak signal applied at the base circuit will be appears in amplified form at the collector circuits. In this way, the transistor will be acts like as an amplifier. Where this based on the device which we are using for the amplifiers, based on the transistor configurations, or based on the input, based on the output, based on the frequency, based on the bandwidth, Based on the selection of the operating point, there are the different types of amplifiers. Now that the classification of amplifiers. One of the classification of amplifiers is based on the active device used in the circuit. If I am using it is a bipolar junction transistors, then it is called as an BJT amplifiers. Or if I am using it is an field effect transistors or metal oxide semiconductor field effect transistors, we have FET amplifiers. So based on the active device used in the circuit, we have different amplifiers. Based on the configuration of the transistor which I am using, whether I am using it is in a common base or common emitter or common collector, we have common base amplifier, common collector amplifier, common emitter amplifier. Based on the input, whether we are operating the transistor amplifier for small signals or the large signals, we have small signal amplifiers and large signal amplifiers. Whereas in this session, we will concentrate more on the active device is the BJT amplifier. We'll use for all the configurations, and also it is only for small signal analysis. A small signal BJT, common base, common emitter, common collector amplifiers we'll discuss in these sessions. And also again based on the output, we have it is an voltage amplifiers or power amplifiers, whether we are amplifying only voltage or we are amplifying both voltage and current, we have voltage amplifiers and power amplifiers. Again, to get the required output, whether we are using a single stage or same kind of circuit we are using for number of stages of same circuit, depends upon that we have multi-stage amplifiers. So again it is number of stages, the amplifiers are classified into single stage amplifiers and multi-stage amplifiers. The other classification of the transistors based on the operating point. If I am choosing the operating point nearer to the cutoff point, nearer to the saturation point, middle of the DC load line, or nearest to the cutoff or saturation regions, so depending upon that whether the output may be available for full cycles or half cycles or less than half cycle or more than half cycle and less than full cycle, based on the operating point selection onto the DC load line, the power amplifiers are classified into different amplifiers: Class A power amplifier, Class B power amplifiers, Class AB power amplifiers, and Class C power amplifiers. Another kind of classification depending upon frequency response, whether the frequency which we are amplifying is in the range of audio frequency or it is in intermediate frequency or radio frequency range, or again it is depends upon the bandwidth, whether we are designing an amplifier for only narrow band of frequencies or wide band of frequencies. There are again narrow band amplifiers and wide band amplifiers. Again there are different kinds of amplifiers, again depending upon tuning. Tuned amplifiers are there. Again if you go for higher classes, and there is a low noise amplifier, high power amplifiers, and amplifiers which are designed for at microwave frequencies. So there are the different kinds etc. are there. So these are some basic classification of amplifiers, where again once again I repeat, so based on that the device used, based on that the transistor configuration is used, based on the input signal, based on the output, based on number of stages, based on the operating point selection onto the DC load line, based on the frequency response, based on it is and the bandwidth. These are the classification of amplifiers. Now let us again, before going to these amplifiers in detail, now we'll look at what is an H parameter model. So before going to the H parameter model, the transistor is a 3-terminal device where it has emitter, base and collector, a 2-port network which consists of or needs 2 input terminals and 2 output terminals. Therefore, the 4 terminals is needed for a 2-port network, whereas a transistor is of having the 3 terminals. If we took one of the terminal of the transistor is common at both input and output, transistor is also acts like as a 2-port network device. So a small signal linear model of a 2-port network will represents now the transistor in active region, how it could be replaced. So that a 2-port network could be modeled of taking it is its parameters. Like if I assume that a two-port network which is of having the two input terminals and two output terminals, and if I assume that the input voltages are V1 and V2 and output voltages are if it is an input and output voltages are V1 and V2 and input and output currents are I1 and I2 respectively, then out of these four terminals, how we are using that the parameters which are dependent or which are independent. Suppose for the two-port network, if I say that V1 and V2 are dependent out of four variables of V1, V2, I1 and I2, if I take it is an V1 and V2 are dependent variables and they are depending upon I1 and I2, where I am assuming I1 and I2 are independent variables. Let us assume that V1 and V2 are dependent variables and these are depending upon I1 and I2 which are independent variables. If I assume like that, then these are called as it will be depends upon a parameters called as Z parameters. Z11, Z12, Z21 and Z22. So, if I take the V1 and V2 as dependent, they are and I1 and I2 are independent, then I can model the two-port network in terms of Z parameters. In similar way, suppose if I take I1 and I2 are dependent and V1 and V2 are independent variables, then they are depending upon like this. It will be depends upon V1 and V2, V1 and V2. They will be depend on the parameters which are called as Y parameters, Y11, Y12, Y21, Y22. So here the two-port network is modeled by taking it is Y parameters into considerations if I1 and I2 are dependent and V1 and V2 are independent. If V1 and V2 are dependent, I1 and I2 are independent, two-port network is modeled by using Z parameters. This is Z parameters and this is Y parameters. Suppose if I take V1 is V1 and I2. V1 and I2 are independent and they are depending upon I1 and V2. If I assume that V1 and I2 are dependent and they are depending upon the independent variables of I1 and V2, then the two-port network is modeled by using H parameters. They are called as H11, H12, H21 and H22. So now in our cases of amplifiers, the transistor is for small signal analysis. It is to be modeled by using these H parameters, where we will consider V1 and I2 are dependent variables, whereas I1 and V2 are independent variables, right? So here the transistor also be used as a two-port network device by considering one of its terminals is common for both the input and output. Then on this two-port network transistor, two-port network could be modeled either by using Z parameters or Y parameters or H parameters because of having more advantages where we can model the transistor by using H parameter model. In the H parameter model, if I assume V1 and I1 are input voltage and input current and V2 and I2 are output voltage and output current, then we can write the H parameter equations of a two-port network device by V1 equal to H11 I1 plus H12 V2, I2 is equal to H21 I1 plus H22 V2. So this is how we can model a two-port network by using the H parameters. So we can model it as an Z parameters, or they are also called as an impedance parameters, or we can model with Y parameters or admittance parameters, or we can model by using H parameters or hybrid parameters. So here in these H parameters, these are the equations. Suppose the H11 from these equations, H11 we can write it as an V1 divided by I1 by assuming V2 equal to 0. V2 is an output voltage. Output voltage is 0 is nothing but, it is nothing but the short circuited. Therefore again H11 is the ratio of voltage to the current. It is called as an impedance. Where it is V1 by I1, it is an input side. Therefore H11 is called as an input impedance when the output port is short circuited. Or this is an input impedance, and it is also written as an HI. HI is equal to V1 by I1, where it is have the input impedance, it is of having the units of ohms. Whereas other parameter H22 from the other equations we can write H22 equal to V2 I2 divided by V2 with I1 equal to 0. Input current equal to 0. Current equal to is 0, nothing but it is an open circuited, and it is a ratio of output current to output voltage. Therefore H22 is named as an output admittance when the input port is open circuited, or it is an output admittance. It is also designated as an H0, where H0 is equal to I2 divided by V2, and it is an admittance where the dimensions of the output admittance is mhos. H12, next another parameter H12. H12 is the ratio of V1 to the V2 by keeping I1 equal to 0. It is the ratio of input voltage to the output voltage. Usually we can call it as a gain is nothing but output divided by the input, but it is a ratio of input voltage to the output voltage. Therefore it is called as a reverse voltage transfer ratio or reverse voltage gain with input port is open circuited, which is denoted with the symbol HR, where HR is equal to V1 by V2, which is the ratios of the voltages. Therefore it has no dimensions. And another parameter, last parameter H21, which is the ratio of output current to the input current with output voltage is 0. Therefore it is a ratio of the currents. It is called as an output current by the input current. It is known as forward current gain with output is short circuited because of output voltage is 0. It is also designated as an, it is a forward current gain because of output by the input. Therefore it is denoted with HF, which is equal to I2 divided by I1, where it is the ratios of the currents and it has no dimensions. Therefore the dimensions of the H parameters are H11, or it is an HI is of having that the dimensions is ohms, where H22 or H0 having the dimensions of the mhos output admittance, where the H12 and H21 are dimensionless, which are voltage ratios or the current ratios. Therefore a two-port network device is modeled with the H parameters of having the 4 H parameters, which are input impedance, output admittance, reverse voltage gain and forward current gain, and those are denoted as an H parameters. So for our amplifier analysis, the transistor is replaced. For analysis purpose, the transistor is replaced with this small signal H parameter model, because the H parameters are of having the following advantages, uses. Where the H parameters, why we are using only the H parameters instead of Z or Y parameters or another parameters, means the H parameters are of having certain advantages or the uses, which are they are represented with the real numbers up to the radio frequencies. So working with the real numbers, it becomes easier. So that is one of the advantages of using the transistor for small signal analysis up to radio frequencies with the H parameters. So Working with the complex numbers is somehow the difficult. Therefore, the H parameters are the real numbers up to the radio frequency is one of the advantages, and they are easy to measure, and they can be measured from that the static characteristics, input and output characteristics of the transistors, and you can determine it. And also they are convenient to use in the circuit analysis and design, and again they are easily convertible from one configuration to the another configuration, and they are readily supplied by the manufacturers. If you go to the data sheets of the transistors, the H parameters of the CE configurations will be given by the manufacturers, and they are readily available. Once you know that the H parameters of common emitter configuration, you can easily convert to that another configurations. So these are certain uses or the advantages of the H parameters. There is a reason why a two-port network or the transistor, a two-port network transistor could be replaced by this H parameter model. Now let us consider we have this and the H parameter equations V1 equal to H11 I1 plus H12 V2, I2 is equal to H21 I1 plus H22 V2. Now if you look at these two equations of H parameter model of a two-port network, if you see that the first equation, voltage is equal to sum of the voltages. It looks like it is an V1 equal to sum of the voltages. So if I understand that the first equation, this equation may be obtained by applying the Kirchhoff voltage law to some circuit to obtain this equation. In similar way, if I look at the second expression of the H parameter model, I2 equal to sum of the currents. So the second equation looks like maybe we have been applied some KCL Kirchhoff's current law to the circuit, so that we have been obtained this equation. So the first equation may be obtained by applying it is Kirchhoff's voltage law to the circuit, and the second equation is obtained by applying the Kirchhoff's current law to the circuit. So now we will see that it is easy if I have a circuit, if you apply it is an easily that what is an KVL or KCL, and we can get the equations. Now I will start to apply in reverse direction. Kirchhoff's voltage law in reverse direction to the first equation to get the circuit, and Kirchhoff's current law will apply in reverse way to the second equation to get the circuit. The first equation I will apply it is an Kirchhoff's voltage law in reverse direction, so that I will look at it and what the circuit diagram I am going to get. This is V1 equal to, I will take the voltage like this. This is V1 equal to plus minus H11 I1, where H11 is the impedance. So across the impedance of H11, there is a flow of current called as an I1. Then I can say that the voltage drop across H11 is nothing but H11 into I1. The other one is plus H12 V2. H12 V2. H12 it is and the dimensionless. H12 is the reverse voltage gain, which has no units. It is only that the value multiplied by the V2 means it indicates that it may be a voltage source. I will take that the voltage source with this polarity is H12 into V2, and I will start this. So now I will apply it is in a KVL for this circuit. Suppose if I apply the KVL, what the equation I will get? It is going from minus to the positive, minus V1, and in the same direction the voltage drop H11 I1, and again it is coming from positive to the negative, plus H12 V2 equal to 0. Or from this I can write V1 equal to H11 I1 plus H12 V2. So I am getting this is a circuit. So if I apply that KVL for this circuit, I am getting the equation 1. So equation 1 represents the circuit diagram which I have been drawn here of having input voltage V1 and input current I1, and there is an input impedance H11 and a voltage source of H12 V2. Similar way, I will apply it is an KCL in reverse direction to the equation 2, where it is an I2 equal to, KCL is nothing but what? If any particular node, whatever the currents are entering equal to the currents are leaving. So let us assume that this is a current I2 entering here, and there is an summation of two components, means it indicates that there is an two branches here. One I will take H21 I1. H21 is a ratio, again it is a dimensionless, multiplied by the current, means it is a current source. So it is, I am calling it as an H21 I1. Another branch is H22 multiplied by V2. H22 into V2. H22 is nothing but output admittance. Admittance is H22. Therefore, I will write this is an 1 divided by H22. And there is a voltage drop of V2. So, I will take the output voltage is V2 like this. So, now if I apply it as an KCL at this node, the current entering equal to the I2 equal to H21 I1 plus the current across this resistor. So, current is equal to voltage divided by the resistance V2 divided by 1 divided by H22, therefore V2 into H22. So, this is an output circuit. This is an output side. I2 equal to is nothing but output side. V1 is nothing but input circuit. So, this is an input. Equation 1 is represents what is the voltage at the input side. Equation 2 is represents what is the current at output side. If I combine these two together, this will be called as an H parameter model of a two-port network device. H parameter model of a two-port network device. So that will show that in this. So this is what it is called as an V1, and through this H11 I will call it as an HI. This is an I1 current flowing. This is an H12. This is an H12 into V2. V2 is nothing but V0. This is what we consider is an the V0. So H21 is nothing. H12 is nothing but HR. This is an HF into I1, and where it is an I2. This is an I2 current, and this is an 1 divided by H22 is nothing but 1 by H0. So this is called as an H parameter model of a two-port network device. So we have it is an these H parameter equations. From the H parameter equations of a two-port network device, we draw that what is the model of a two-port network device with H parameters. So therefore it is called as an H parameter model of a two-port network device. H parameter model. Now I will use this H parameter model for transistor. And again transistor acts like as a two-port network device. If I take any one of its terminal is common for both input and output. If I take the base is the common base configuration. If I take emitter is the common emitter. If I take it is an collector is the common collector configuration. Now we need to draw that taking the transistor as a two-port network device, draw that the H parameter model of a common base configuration, common emitter configuration, common collector configuration. Let us suppose I am taking it in a common emitter configuration. So means common emitter is nothing but emitter is the common for both input and output. This is an emitter terminal which is common for both input and output. Base is the input terminal. Collector will be becomes output terminal. So if the base is the input, what is an input voltage will be becomes VB is the input voltage. What is an input current? It becomes IB is an input current. If collector is the output terminal, IC will be becomes as an output current. If collector is the output terminal, VC will be becomes as an output voltage. So here V1 will be replaced with VB, V2 will be replaced with VC, I1 is replaced with IB, and I2 will be replaced with IC. And again it is in a common emitter configuration. General H parameters are, we have HI, H0, HR and HF. These are for general two-port network. What are the H parameters? If it is a common emitter configuration, we will write these H parameters specific to the common emitter configuration by adding in suffix one more letter called as an E. Therefore, HIE, HOE, HRE, HFE will be becomes as an H parameters of common emitter configuration. So in the same, this is the model, H parameter model. I will replace wherever the H parameters HI, HR, HF, H0 are there. I will replace with the H parameters of CE configuration. Wherever V1, V2, I1 and I2 are there, I will replace with VB, VC, IB and IC respectively. Then see that what is the hybrid model or H parameter model of a two-port network by using the transistor as a two-port network device, where in common base, first diagram will be represents that in common emitter configuration, this is for common emitter configuration, and the second one it is for common collector configuration, and the third one is for common base configuration. Equations are the same, only that the H parameters are represented with respect to that particular configuration of CE. We use it as an HIE, HOE, HRE and HFE. Whereas if it is an CC configuration, suffix instead of E I can use as an C, that is HIC, HOC, HRC and HFC. If it is a common base configuration, I can use HIB, HOB, HRB and HFB. Similar way, depends upon that the common emitter configuration, the input and output voltages, input and output currents are changes, common collector, and again it is depends upon that. If it is a common base configuration, emitter is the input, therefore VE is as an input voltage and VC is an collector is the output, VC is an output and emitter is the input and IE is the input current and IC is an output current. Therefore, these are all the H parameter models of common emitter. For common emitter, VB is an input voltage. For common base, VE is an input voltage. So, these are the H parameter model. Right? So, in this session, the dear students, in this session, we learned about what is an amplifier and where the operating point to be chosen onto the DC load line to get the stable operating point, and with respect to that the thermal stability, what is the condition which we need to use, and again to get the faithful amplification, how the operating point to be chosen onto the DC load line which we have been seeing, and again the transistor analysis as an amplifier analysis. To do that, the transistor should be modeled with respect to the H parameters, and why we need to use a H parameter model for a small signal analysis of transistor amplifiers, what are its advantages we have been seeing, and also we have been modeled or we have been learned how to draw that the H parameter model of a two-port network device by knowing that the H parameter equations, by applying KVL and KCL in reverse directions, and how we can apply those the general H parameter model to our two-port network transistor, and again the transistor by taking in common emitter, common collector and common base configuration, how we can draw the H parameter model of a common emitter configuration, common collector configuration and common base configuration by representing the H parameters of CE, CC and CB H parameters. That's what which we learned in this session. Thank you, and we'll go ahead in the next session to discuss about in detail what are the analysis of those the transistor amplifiers. With respect to that, the general analysis will do that by taking the H parameter model of a two-port network by considering how to do the analysis parameters which are called as the AC analysis parameters or the amplifier analysis parameters which are called as how to calculate its current gain or voltage gain, or it is an input impedance or output admittances values which are called as the analysis parameters of an amplifier. How we can do that, those are AC analysis of an amplifier and the general parameters how we can calculate, and we'll discuss in the next session. Thank you so much. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.